Hey everyone. So I'm JJ with Purse, and tonight I wanted to talk to you about full nodes and full node implementations in general, but particularly my project and the project we've been working on at Purse, which is Bcoin. And so a little history about me is I've actually given a presentation here before, like 2 years ago at the Dev Meetup, and what I gave my talk on 2 years ago was actually the process of turning Bitcoin D into a shared object, into a library, so that you could link to it and call functions directly and call consensus code. And it was a very small change. It was like just a small compile time option, a couple line change to the config file, and I submitted it as a pull request to Bitcoin Core, and it got rejected. Like unilaterally by everyone. So now I'm here 2 years later, and since I had no options left, I wanted to do cool Bitcoin things. I wanted to have a cool library to do it. I wanted to have a library that could be a full node. And since I couldn't use Bitcoin Core, I just ended up writing my own full node library. So here I am 2 years later, and I'm going to present that. So Bcoin. What it is, a little history about Bcoin, is it was created in 2014 by Fedor and Dutney. He's a lead node.js dev. You may have heard of him. He was actually the guy who discovered that you could actually steal a private key from a Heartbleed infected server. He was the first one to actually prove that. He's a really smart guy. And when he created Bcoin, at that point in history, in 2014, I was sort of into cryptocurrency. I had been like mining, I tried to mine Bitcoin, it didn't work. I tried to mine Litecoin, eventually Dogecoin, but I didn't really understand it. I would look at blockchain explorers and I would see this Merkle root thing and I would be like, okay, what is that thing? Why is it there? Why is it necessary? And I tried looking at the Bitcoin decode, and I think I looked at it for about 2 minutes before I was like, okay, this code is horrible. There's no way that anything clever or good is in here, and I just gave up reading it. And so my friend Fedor created this simple SPD wallet in the browser called Bcoin. And the first time I was familiar with Fedor's code, so I thought I'll take a look at it. I'm interested in cryptocurrency and stuff. And the first time I read through it, and I saw how a transaction verification worked. Yeah, I think it was actually the first time I started to understand how Bitcoin worked. And it was, it was brilliant. Like I saw everything. Okay, the previous output script is included in the current transaction, and the previous transaction ID is included in the current transaction. That affects the current sighash and the current transaction ID. Okay, that's brilliant. Actually, I didn't see this in the Bitcoin decode because it was just, full of all this shit. And you can't read it. It's unreadable. But when I saw it expressed in a simple way, I was like, oh my God, it's a brilliant protocol. It's a brilliant way of doing things. It's just implemented horribly. So I became a contributor to Bcoin right away, and it was still a simple SPV wallet. And last year I started to rewrite it as a full node. And it was originally for use in, well, the thing that really pushed me to rewrite it as a full node was for use in Purse.io, but it's an open source project and anybody can use it. And I think we do need alternative full node implementations. So I'm going to step back from Bcoin for a little bit and just talk about alternative full node implementations in general. Okay, so Bitcoin D, or Bitcoin Core, it was the first implementation of Bitcoin by Satoshi. So there is this, it's really old and it's full of a lot of old code and stuff like that, but one thing it brings with it is actually a mentality. It brings a lot of baggage. So there's this long-standing mentality that it is the only full node and that it is impossible to re-implement. So there's a quote from Satoshi himself up here where he says, and I quote, "A second implementation would be a menace to the network." And this is actually a very popular opinion. People are very opposed to alternative implementations.
Matt Corallo, as you can see there, he very nearly has like a mental breakdown describing his opposition to alternative implementations. And then there's a quote from Peter Todd there, and he's Peter Todd. I wouldn't have him any other way. Okay, so we have some pushback here. We have a lot of people who think this really isn't a good idea, and while their opinions do have merit, I think they're very dismissive. They say it can't be done, and they haven't really tried to re-implement it. They haven't waited to see whether an alternative implementation can actually pull this off. They just assume it can't be done. Even Satoshi, if you actually read the rest of his post, it's actually more that he's lazy than anything. He just didn't want to help maintain an alternative implementation. But he doesn't say it's impossible to re-implement. He just says it's a menace. So moving right along. Straight up menace. So I'm going to be referring to alternative implementations as menace implementations. So there's a few menace implementations out there. And these are not all of them, but these are the ones that maybe are seen as the most production ready. So there's Bitcoin J, which is written in Java, and it's really bad. And then there's BTCD, which is written in Go, and it's fantastic. It's a really good project. And then there's nBitcoin. I actually haven't played around with it much, but it's the .NET stack. It's C# and it's also really well written. And now there's Bcoin, which is JavaScript. And there's never really been a full JavaScript Bitcoin node. There was Bitcoin JS a couple of years ago. And they had Bitcoin JS server, which would actually connect to the network and try to validate the blockchain. But they ran into a lot of issues with scalability and data management and things like that. So the project was actually abandoned in 2013. But the guys who write it are actually really smart. I want to make that clear. The CryptoCoin JS guys, they do great work. It's just that project is now unmaintained. So there's never really a good thing in JavaScript to do Bitcoin with. So we can ask ourselves, if this opinion is so unpopular that it's really bad to have an alternative implementation, why are all these menace implementations popping up? And MC8 can answer that. He points to childhood. He says that childhood is the reason that these menaces are created. So maybe it's Bitcoin's childhood that's to blame for these menace implementations. So let's look at Bitcoin's childhood for a second. So Satoshi releases a white paper. You all know that. He releases a working C++ implementation of his protocol. The implementation itself has no tests, no docs, and it has global state riddled everywhere. And that last part is really important because global state means that it's almost impossible to abstract things out and turn it into a library if you have global state in the process. It's not instanced. It's not unique to one instance. So it was meant to be a process. It was not meant to be a library. So here's basically sort of a list of the Bitcoin D shortcomings. So global state, went over that. Very poor coding style. It's already C++, right? But it's like on top of that, you have extremely weird code, and just it's not very readable, and it's especially not readable to beginners who want to try to understand Bitcoin. If you've never read the Bitcoin decode and you go and read the master branch and you can actually understand it, congratulations, you're a liar. You didn't understand it. Nobody's going to understand it. So aside from the poor coding style, a very cumbersome external API, especially for notifications. And I just want to say Mike Kern was right on one thing. So in 2014, he had his Bitcoin XT thing. He really wanted to implement this new message on the network layer called get UTXOs. So light nodes, like SPV nodes, don't usually have access to the full UTXO set. And the UTXO set is pretty important because you almost can't do anything interesting in Bitcoin without the UTXO set. You can't verify transactions. You can't see the value of transactions, at least the value that's being redeemed. So wouldn't it be nice if these light nodes had a way to just ask the network for UTXOs, and that way they don't have to maintain an entire blockchain? So it sounds good on paper, but it's actually a really bad idea because right now there's no cryptographic proof for UTXOs, so you have no idea whether a node is lying to you about values or scripts or anything like that. So when this blew up in his face, and he didn't write proper tests for this implementation and ended up being a DOS vector, you know, he was overly defensive about it. He didn't just admit that he was wrong. He was basically a total asshole about it. But he said one thing that was totally irrelevant, but made perfect sense. It was irrelevant, but it was absolutely true. He said, whoever Satoshi was, he showed no familiarity with post-1995 software development techniques. And then that includes a complete lack of any unit tests and therefore a testable code base. Any modern implementation should do better. You cannot currently build fake chains, blah, 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 blah. So he made a really good point there. I wish more people would point this out. It's a shame that I have to quote Mike Hearn here. Like, I wish somebody else, like, I actually wish somebody else said this, but I have to, and I have to say he's right. So now, you know, that was like 2014. We went over the child a little bit. So nowadays things are better. What's changed? Tests. There's lots of unit tests and things like that. There's actually really good docs and just docs on the Bitcoin protocol in general. And it actually explains a lot of how it works. There's libBitcoin consensus, which is, I mean, the goal of libBitcoin consensus is to move a lot of consensus functions out of Bitcoin and into a library so you can just link to it and call these consensus functions, and you don't have to worry about compatibility with consensus. So the problem with that is that it's just the scripting system, so it handles only a small part of what Bitcoin consensus is. There's actually a lot of other stuff you need to check. So it's a step in the right direction, but it's in practice, it's probably not that useful until more functions get in there. There's more fleshed out API, more RPC calls. There's a REST API now. So what hasn't changed, there's still global state all over the place. There's like this insane system of locks you have to use to access the coins. Am I right, roast beef? Am I right? Yeah. Code insanity hasn't changed, and I'm gonna talk about that in a second. Notifications, there's still really not a good way of doing notifications. There's a wallet notify argument you can pass in, which will actually spawn a child process every single time a transaction comes in. And while that's a really Unixy way of doing it, it's also a really ugly way of doing it. It's a really slow, inefficient way of doing things. And then there's some 0MQ notifications too. And it's still written in C++, unfortunately. That hasn't changed. So here's I mean, if you have a weak stomach, you might want to look away. Here's some sample Bitcoin decode. And this is actually SegWit code. So what this function is doing is it's looking through a Coinbase's outputs to find the commitment output. And the commitment output is sort of a special thing you need with SegWit. And so, yeah, there are two problems with this function. One is that if statement is 354 columns. It's wrapped here, but it's actually on a single line. And yeah. And then you notice that the for loop actually doesn't break when it finds the commitment position. So that means that every commitment position before it is actually ignored. So that's sort of a weird way to write it. You might want to start like backwards and go back and then break when you find one. So it's not immediately obvious what it's doing to somebody who wants to re-implement this code. And so this is, I actually want to clarify something. This is Peter Villa's code, and I actually love SIPA, I love SegWit. It was a lot of fun to implement. I think he's a really smart guy and a really smart programmer. This is just the example that came to mind when I wanted to show how horrible the Bitcoin decode is. But this is not the only example. I don't blame Peter Villa here. I blame the overall coding style of the project. Because if you look at Peter Villa's project, libsecp 256k1, like the code there is brilliant. But I think there's some spell that Bitcoin Core has over people that when they contribute to it, they just write really ugly code. Okay, so let's make something better, something more readable, more hackable, more maintainable. How do we do that? So there are some hard parts to doing this. First is the vastness of Bitcoin. There's a lot of different things happening in Bitcoin. There's a lot of different features. And the second is the complexity. Is not only are a lot of different things happening, these things that are happening are actually very complex and very hard to understand. And then the third thing is data management and scalability. So people probably don't realize how much data management Bitcoin actually is. There are tens of millions of transactions, hundreds of thousands of blocks. It's an insane amount of data. So you really, really have to focus on data. If you work on a Bitcoin full node, it will actually get you interested in databases because you have to find the most optimal solution. And then the fourth, the really tough guy, is consensus, agreeing on all consensus rules. And then the fifth thing is transaction relay policy, which is sort of like consensus, but not as important because you're allowed to get it wrong. It's okay if you screw it up a little bit. Oh yeah, and then I have a really cool quote by Al Pacino there. I think it's really cool. It makes sense, right? You can't learn about it in school. You can't learn about Bitcoin in school. You have to just dig into it. So let's examine. So I sort of explained vastness and complexity, but let's start with data management and scalability and what that requires. So data management in Bitcoin, there's coins everywhere. And when I say coin, I mean UTXO. I call UTXOs coins because I think UTXO is a really ugly acronym and coin just makes more sense. So coins are the heart and soul of Bitcoin. There's currently 40 million coins and 11 million unspent transactions. So this is sort of a problem. We need to store all these coins and we need to index them in some way. But every key in a database can potentially make another key look up slower. And coins also generally need to be cached in memory for fast access. They need to be future-proof because we don't want to have a giant migration if we need something else, another piece of data from the transaction. They also need to be compressed. So unlike the actual blocks in the blockchain, the UTXO set cannot be pruned. It can be pruned when you spend the coins and then you delete those, but you need to maintain a full UTXO set. Blocks you can prune to, you only need to keep the last 288 blocks, but UTXO set, you need the full thing. So it's in our best interest to keep it compressed and keep it as small as possible. If the UTXO set became 80 gigabytes, and maybe it will one day, it would be almost pointless to have a full node that's pruned because you still need to store the UTXO set. So indexing versus UTXO ID versus TX ID. So I was going to explain to you why Bitcoin J is horrible, and this is why. So there's sort of a UTXO ID thing, right? And it's the hash of the transaction plus the index of the output. And that's the way Bitcoin J indexes coins. So that means Bitcoin J has 40 million keys in the database for the UTXO set. The other way to do it is to store it by transaction ID. So this is actually a really cool thing about Bitcoin not too many people know about, which is why I wanted to share it with you, is there's actually sort of like a fundamental primitive data structure internally used in internal implementations of Bitcoin that are sort of a coin serialization. They're very similar to a transaction, but they only contain outputs and the version and usually like a Coinbase flag and some other things. And so it's like this, this thing is found everywhere internally in Bitcoin implementations, but not many people are familiar with them because they don't show up, on a blockchain explorer. They're not external. So that's the way you store it. You store it under the transaction ID, but you only store the outputs, and you delete the outputs once they're spent. And the blockchain, when it can't find an output, it just assumes it's double spent. So there's another thing that Bitcoin J doesn't do, and so there's something called a coin viewpoint, and this is also sort of an important internal data structure in full nodes, is that a coin viewpoint is sort of a snapshot of the entire state of coins as they pertain to a block, and that block could be getting added to the chain, or it could be getting disconnected, like during a reorg. So some of the coins in it could be spent, some could be unspent. So it's a really necessary thing to have, and I wanted to point this out. This is what you need to do if you want to make a full node, and Bitcoin J doesn't do this. So I thought I'd point that out. So if we can get all this data management down, what's next is the blockchain and mempool. So the blockchain is very neat and organized. Everything comes in order. It's easy knowing whether a transaction exists or not on the blockchain. If it's not on the blockchain, it doesn't exist. The mempool is in many ways trickier to implement than the blockchain. I call the mempool the Wild West. There's orphan transactions, and in those orphan transactions, the transactions they're redeeming, we actually can't check whether those transactions exist or not. We can't check to see whether we simply haven't seen a transaction before, or whether that transaction is just non-existent. So it's really weird to deal with. So you need to store orphans when they come in and hope they get resolved eventually. And if they don't, you need to drop them out of the mempool. And in the mempool, malicious transactions are more common. It's not very easy to forge blocks and craft malicious blocks, because nodes always verify the headers first. It's very hard to fake even just headers. It requires a lot of effort. But in the mempool, it's really easy to forge transactions. And then the next thing that's hard about the mempool is these transaction relay policies. Like I said, they're not consensus rules, so you're allowed to get them wrong, but they're still very hard to implement. They're very tricky, and because they're stricter than consensus rules, they're easier to get wrong. So consensus, like Satoshi said, lockstep. So in Bitcoin, bugs become consensus rules, and that's because we're not Ethereum. We don't, yeah. It sounds like a joke, but I'm dead serious. We don't just we don't roll back history and hard fork just because we find a bug in the protocol, or a bug, much less a bug in a single script, right? We have integrity. We just live with it, and it becomes a consensus rule. So one of my favorite examples of this, just to explain how weird this is, one of my favorite examples of this is something Peter Todd brought to light on the dev mailing list a little while ago, or like 2 years ago. So this is one of the coolest transactions ever sent. It only exists on the testnet blockchain, but the first funding transaction that sends to something, if you look at the first output, you can see it's sort of a regular 202 multi-sig, but it has some other stuff before it that's kind of strange. And then the transaction that redeems from it, transaction 2, input 2 is redeeming from output 1 of transaction 1. And that just looks like a regular multi-sig input. But if we go back and look at output 1 from transaction 1, we notice that there's a signature in it. And if you look at it closely, that signature is actually valid. So we have a valid signature for the next transaction in the previous transaction output. And if you know how sig hashing works, you should know that this is logically impossible, short of a hash collision. It is not possible. So what the hell is going on here, right? Why is there a valid signature in the first output? So chicken or egg. This is a chicken or egg problem, right? If you a signature is basically a hash, like an encrypted hash. So how could you have a hash for the next transaction, the previous transaction is the question. So in the original Bitcoin implementation, there's different sig hash types in Bitcoin. Everyone is used to sig hash all, but there's also a sig hash single. Sig hash types hash the transaction differently when they're creating signatures. And so what sig hash single does is it only signs the output at the current input index for the signature you're creating. But the question is what happens when the input index is actually higher than the number of outputs. So as I showed here before, there's so So there's two inputs in the second transaction, but there's only one output. So when it does sighash single on the second input, what happens? Well, this happens. If you notice, it returns a 1, but this function is returning a uint256, which is a 32-byte hash, a SHA-256 hash. So when it turns a 1, it gets cast to a uint256. It's actually pretty interesting. This is one case where explicit typing actually hurts you more than it helps you. If you were to write this in JavaScript, the code would just throw, but in C++, it actually hurts, ruins consensus rules. So because of this, this bug, this results in a predictable signature hash of a 1 followed by all zeros. So we actually know what the hash is ahead of time, regardless of what the hash of the next transaction is. But even stranger is that there's this find and delete thing. So whenever a check sig happens, the way Satoshi originally wrote it, or a check multisig, is that find and delete gets called on the signature being verified, and it goes through the previous output script trying to remove the signature from that previous output script. And for a long time, people thought that code would never get called and had never been called on the main chain, because how could a valid signature be in the previous output script? What is the purpose of this? So, I mean, people were probably right. This should never get called. But because of sighash single, we can actually have signatures in previous output scripts, and they will go back and remove the signatures from the previous output scripts. So if you look back at this transaction, it's a multi-sig transaction. So there's another regular sighash all signature in the input. So when that signature is created, you need to take into account that the signature and output 1 from transaction 1 is actually going to be dropped from the script when it's signed. So that's one thing you need to take into account. All the other signatures need to take that into account. And if you don't get that right, byte for, I forgot to mention, the signature is actually reserialized as it's passed into find and delete. You notice it's passed into the C script constructor, so it's changed to a single push data. So if the signature in the previous output script is not the same push data, it won't get removed. And you also need to account for that. You need to get this down byte for byte, exactly, or you'll get forked off the main chain. So you know, some of these opinions that it's impossible to re-implement a full node, like I said, very dismissive, but they sort of have some merit, right? This is just insanity. So if we can get that right, maybe we can move on to transaction relay policy. And so here's an example policy edge case. So recently it was discovered, after SegWit was merged in, that witnesses can be mutated as their relay. A bad actor on the network can mutate a witness and give a really big witness or an invalid witness and cause validation to fail on some level and get passed in this recent rejects filter thing. The recent rejects filter is a Bloom filter that keeps track of all the transactions that have been recently rejected, so you don't re-request them. And so it tracks by regular transaction ID, which is the problem, and not witness transaction ID. So if somebody mutates the witness, it doesn't change the regular transaction ID. So somebody can take your transaction, alter the witness, and your transaction gets added to the recent rejects filter, and it effectively censors the transaction until the next block. The recent rejects filter gets reset every block. And so Johnson-Lau's solution, there's sort of like a crappy, naive solution in Bitcoin Core right now. Johnson-Lau's solution is bad witness, which is a good solution. It checks for standardness of the witness vectors and whatnot. And but you know, at the end of the day, I mean, you have to get relay policy right. It's a whole bunch of nonsense, and it's a whole bunch of work, and it's a lot of things you need to focus on getting right. And but you know, if we can do all of this, if we can get past this and re-implement consensus and policy, we now have a framework to actually build a good Bitcoin library on top of. So that moved me on to Bcoin. That's that kind of stuff I've been doing. I know it's really boring, but that's the kind of stuff I've been doing for like the past year. And I've been sort of obsessed with it. So I think I did a good job of re-implementing it and thinking about how to re-implement things. And so this is Bcoin. These are some code examples. This is what Bcoin looks like when you require it. So we can create a blockchain technology for your blockchain app. And you notice that there's no global state here. You instantiate a new blockchain, and you can get the Genesis block and whatever. But there's no global state, so everything there is self-contained within that instance of the blockchain object. So that's really handy. And Bcoin itself only has two required dependencies by default. There's no like left pad stuff going on in here, if you guys are aware of that whole drama. It's only two dependencies. So you don't even need a database. By default, Bcoin will actually create this blockchain in memory. So you can create, hundreds of these things. You can have them on different networks. You can do whatever you want. And then syncing the blockchain, you notice you pass the chain into this pool object. And the pool is the peer-to-peer pool. It's the network pool of peers. And then you can start the sync. So what's important about this is that these two objects are not by default tied together. You don't instantiate them together. They're totally separate. So you can have a blockchain without a peer-to-peer pool. You can have a peer-to-peer pool without a blockchain. You can have, you can actually have a mempool without a peer-to-peer pool. You can have a wallet database without any of that. It's all a loose coupling. It all sort of works on its own. And so the way we deal with this is that we have all these sort of cool objects like peer-to-peer pool and blockchain and whatever. And they're just all tied together by this full node object that Bcoin has. So the full node code in Bcoin is actually very small. It's just a proxying of events and tying all these different objects together. Whenever the pool receives a block, it notifies the chain, receives a transaction, notifies the mempool, and so on. And then when the wallet data, you can also notify the WebSocket server. We have WebSocket events in this system, and it's all very uniform and it's all very clean, and it's very easy to reason about. Okay, so a lot of people ask this question: why JavaScript? So first of all, I want to say is that JavaScript may not have been a totally conscious decision in Bcoin's design, since it was already written in JavaScript when I got involved. But I actually think it's a better language than most people probably think it is. It's faster than you think. It's actually pretty damn fast, which is surprising because JavaScript is such a dynamic language. On benchmarks, it can't compete with, say, Go or something. You can maybe come close and select benchmarks. But it'll beat the hell out of Ruby or Python or something. It's really.
Is this with the ASM.js subset, or is this just JavaScript in general?
No, I'm just talking about JavaScript here, man. just V8 JavaScript. Yeah. So the other benefit is that JavaScript is ubiquitous. It's everywhere. Everyone is familiar with it. Everybody's seen it at some point. It will, run in the browser, on the server, on your laptop, on your phone. So no other language platform can lay claim to that except for JavaScript. And yeah, server-side, browser-side, went over that. So Bcoin actually runs in the browser. You can actually sync a full node on main in the browser, and it will store the blockchain in IndexedDB, and it will do full validation in the browser and maintain a mempool and everything. So the drawbacks to JavaScript is that there's no 64-bit number types. I actually think this is one of the biggest problems with JavaScript. This is just a huge pain in the ass. So you need to sort of hack into the language. So JavaScript only has double floats, so we got to figure out some way to deal with that. JavaScript is only single-threaded. You have asynchronous jobs or functions that are asynchronous by default, but there's no convenient way to just put something on another thread and just use it asynchronously. So we got to figure out a way to deal with that. And the third one is people aren't used to writing real code in JavaScript. They're just used to spinning up node.js and serving a web page and hitting MongoDB and then serving another web page. And then in the browser, they're just using Angular and React. It's like it's not even JavaScript anymore. So not many people actually know JavaScript, at least not the kind of JavaScript that Bcoin is written in. They're familiar with it, but yeah, we need to introduce more real code into the ecosystem to get people thinking about JavaScript more deeply again. So yeah, solving these drawbacks. We can use a lot of trickery to treat doubles as though they were ints. And it's possible, it's time consuming, but if you know how ints work and you know how doubles work, you can actually make JavaScript behave as if it has ints. And precision loss. So double floats lose precision at 53 bits, which is actually pretty lucky because max money in Bitcoin is only 51 bits. And a 51-bit max plus a 51-bit max, the highest it can be is 52 bits. So we can check for value overflows in consensus code the same way Bitcoin Core does, or the same way any consensus implementation would do. If we're adding up output values, we just check that the first output value is less than max money, and we check that the second one we're going to add it to is less than max money. We add them together, and we check that the result is less than max money. And that works because we're never going to get a result higher than 52 bits and lose precision and potentially have a bad comparison. So JavaScript is single-threaded, so we can solve this by using worker processes in Node.js and worker threads, or web worker threads in the browser. And it actually works pretty well. So, if you have 4 cores, you can spin up 4 worker processes in Node.js, and you can verify 4 transactions at the same time. You have a block that comes in, you can parallelize transaction verification. So yeah, for the not much real code in JS thing, we need to make JavaScript great again. And this is what Bcoin is trying to do, and this is also what Ryan Charles at Yours Network is trying to do. We're going to make JavaScript great again. We need to get some real code back into that ecosystem, because it can't all just be Angular and React and MongoDB and just all this bullshit. Oh, okay. It's time for my example. So I would like to show you how some of this works in Bcoin. Let's see. Bear with me here. So what I'm going to do is I'm going to go into the Node.js repo, and I'm just going to require Bcoin and do some things with it. So I can instantiate a blockchain just like that, and that's in memory because I haven't selected a database. So if you look here, you'll notice that it's just, it's just stored in a red block tree in memory. And so now that the chain is open, I can do, typing with one hand is hard. I can just request, the Genesis block from the chain database. And so there we have the Genesis block. And so we can take this blockchain thing. Can you guys still hear me? I'm trying to yell into the mic. So we can take this, like I said, we can start up a peer-to-peer pool, and we can pass the blockchain into it. And I'm going to bind to the error event so we don't get spammed. Okay, so now that we have this pool thing, and it's tied to the chain, we can open it, and we can start the blockchain. Actually, first we can connect, and you'll notice that when you connect, it doesn't try to sync the blockchain. Let me up the log level here. It doesn't try to sync the blockchain or anything. It just starts requesting transactions and things like that. We don't really have a mempool, so it's not actually relaying transactions, but we can request transactions perfectly fine. And all these messages will be emitting transaction events on the pool. Let me turn off the logs here real quick. So now we can start the blockchain sync. Okay, apparently we don't have a good peer here, or I don't have a connection. Okay, there it goes. Okay, so there's us syncing the blockchain. And, that's all stored in memory, so it's probably not good to sync it too much. So I'll turn these logs off real quick. So that's how easy it is. We can start up transactions, we can create mutable transactions, we can add inputs and outputs. I actually don't have any funds right here, so I can't show you sending a transaction, but I will show you receiving a transaction in a second. So that's cool. So let's. So I have the main chain synced on here on Bcoin, so I'm going to start that up now. So it's just a simple command line, and here we are. We're on the network, and so Bcoin. One of its goals is to have a nice API, but another one of its goals is to be compatible with Bitcoin D. So it includes a legacy JSON RPC system, so we can do things like get blockchain info, and we have the same output we receive from Bitcoin D. We can do get peer info, but there's also sort of like a new school API aside from just the RPC. Because we don't want to clone Bitcoin D completely, because that's what we're trying to get away from. So the new school API is accessible through CLI. So we can access the primary wallet, and we can ask for the balance, for example. And, oops. And so Bcoin's wallet is a BIP44 wallet, so we can look at that, and we can see the address and the token and whatnot, and the current receiving address. So one of the things I like to do, just to prove to you guys that this is a real wallet and a real node, I would like to send a transaction to myself. If that's okay with you guys? If my phone works. Oh, yeah, that's fine, I don't care. I'll move it out of here in a second. I should have done this on testnet, I knew it. If someone can actually import that and rescan the chain that quickly, I'll be very impressed. Seriously, try to do it. Okay, so if we just so yeah, it will actually return the mnemonic to you by default if it's not encrypted. So it's probably good to encrypt your wallet. Apparently I didn't learn that lesson. Okay. Yeah, so my phone is dead and my camera is dead. If anyone wants to send me money, though, here's the QR code. Anyone want to send me a tip for having a really good talk? We can watch the events here. Anybody? Anybody? Oh, I bet. Shit, where did I put it? There it is. Oh man, I'm gonna get a lot of money. This is really good. All right, so. Okay, so yeah, right there we can see you know, incoming transaction from one wallet. And another incoming transaction. Thank you, whoever that was. The QR, what, more people want to send me money? You know, all this money is going to get stolen in a second. So it's like, you can steal back your money if you want. Let me clear that. Let's see if more money's coming. Oh. Okay. Oh, shit. Not again. Okay, so, you know, we can look at the history and... Oh, is that you? You're famous. And holy, wow, we got 3 transactions from you guys. That's pretty good. Yeah, so if anyone wants to steal this, this is the amount of coins you'll get. You'll get that many. And I'm going to move that out as soon as I stop working on this. Okay, so that's Bcoin right now. And I hope I've made my point that it's actually pretty easy to use. You can even just go into the node.js repo and just you know, just create a blockchain like it's nothing. The other kind of cool thing is so right now Bcoin has a lot of features. It's up to date with a lot of the latest BIPs. So like version bits, SegWit, compact block relay. But one of the really cool things it supports that actually nothing else supports right now is BIP 150 and BIP 151. And those are the peer-to-peer encryption and peer-to-peer auth BIPs. And I actually think those are really cool and really necessary for Bitcoin. Bitcoin ideally should have had it from day one. Lightning has it from day one, but Bitcoin does not. So it's great to get that into Bitcoin right now. And so that's one of the really, so if, yes, in the back.
I'm curious if you yourself are planning on proposing features to Bitcoin Core itself.
Not right now. I don't have any good ideas right now. I'm more about re-implementing it in a sane way. But yeah, I mean, I'll keep my eyes open.
I'd like to see your CLI working with Bitcoin.
My CLI working with Bitcoin D. So, sorry, what do you mean by that?
Being able to have those same output, same more output choices.
More output choices. You want to see more RPC commands? Is that it? Okay, what would you like to see?
More of your command line.
Oh, right.
I think you mean like extend instead of improving with similar CLI parameters.
He wants to see it before.
Yeah.
Oh, yeah. So, I mean, yeah. I mean, one of the nice features that could be added to core would be WebSocket support, but at the same time, I almost feel like maybe it doesn't belong there because it's so you would need to decide on a protocol for doing it. So right now, Bcoin uses Socket.io, just Socket.io events, which is actually a pretty simple protocol. I mean, it would be nice to maybe have something like slightly more low level in Bitcoin Core. So I mean, that would be a pretty nice extension. That would be a pretty nice extension to Bitcoin Core, and maybe more extensions to the REST protocol too, to the REST API, because right now it's just all RPC where you just pass in parameters as like a JSON array, and it's very annoying to just sort of like curl it for that reason. It's not very just usable on the command line for that reason. So yeah, so now that we have Bitcoin full node in the browser, we can also do other cool things like layer 2 things, as they say. So right now Bcoin has the start of a Lightning implementation being built on top of it. It's called Plasma, and it's meant to be LND compatible. So right now it can connect to the network and do the initial handshake and send a single funding request and But the data management isn't quite there yet, and I hope to get it there in the future. Because Lightning is very cool, and it's very fun to work on. So that's about it. Oh, wait. So yeah, so this is a movie that... So this is a movie that me and Roast Beef are going to star in. It's called Menace to the Network. It's like a sequel of Menace to Society. And yeah. And yeah, so the movie was inspired by Satoshi's quote. And that's us, looking pretty gangster. Okay.